Hello everyone. I am Başak Küçük. This was my first time to being mentor here. First of all, I would like to thank organizer committee to organizing this nice program. And my mentee, Doran Pamukçu, he's an undergraduate student in Boğaziçi University. He's studying both mathematics and computer engineering. And today he will be talk about Lefschetz fixed point theorem. Thank you.
Thank you, Başak. I want to first say that this will be an algebraic topology presentation. And we're going to do this theorem and talk about it. Let's get straight into the theorem statement. Is that FF be a self-map on a finite simple complex, or more generally, a check of a finite simple complex X. If the Lefschetz number LF of the F star, which is the induced function on the homology groups, is non-zero, then F has a fixed point. There may be some mathematical terms that are unfamiliar to you right now, but my goal in this presentation is to explain to you all of them. So first of all, why do we even need this fixed point theorems? As this is a topological proof, this theorem does not tell us any method to find the location of the fixed point, because we usually investigate spaces out to homotopy, but even the existence of it can be helpful. For example, to prove there's a Nash equilibrium in game theory, when there are finite layers and finite option spaces, we can use this Doran fixed point theorem, which is another fixed point theorem that I will be talking about this presentation, or Lefschetz fixed point theorem as well, to prove there exists a Nash equilibrium. And first of all, what is a homology? We're gonna use this topological invariant a lot in this presentation. It is a topological invariant again that encodes the different dimension holes in a space using abelian groups, and there are many versions of it: simplicial, singular, cellular, and etc. Here's a quick remark: homotopy equivalent spaces have isomorphic homology groups, as it's a topological invariant. This is what we expect, and this is the homology groups, simplicial homology groups of our torus, which is an empty donut if you don't know. It looks like this, and we're gonna actually calculate these groups, calculate the simplicial homology groups here now, right now. First of all, to calculate the homology groups, what is a finite delta complex? We're gonna need this structure. It is a space built using finitely many simplices. So as a simplex, well, the zero dimension simplex is just a point. One dimension is just a line. Two dimension is just a triangle, and tetrahedron is the third dimension version. It goes like this. We can embed the nth dimension simplex into Rn plus 1 using this formula. And like a really basic form of topological space. We can use this to build spaces. And here's the torus, the delta complex structure of the torus. As you may know, it is very similar to its planar representation, but we have this additional C1 simplex here in the middle to make things triangulized. It's like really, but also there are like two simplexes, U and L, two triangles. And using this, we're going to calculate the homology groups of the torus. So, okay, we need free abelian groups. How do we define them? Well, for any n simplex, we're going to just take it as a representative, and we're going to construct a free abelian group. So our elements of our groups are called n chains, and they look like this. These ENs are just simplices. And you can write any element with this one, where the coefficients are integers. And using this abelian group, now we can define a boundary map, which reduces the dimension 1 by 1. And its definition looks like this. It's just an alternating sum. And the head notation means that you just delete that vertex. So what do you get? If you delete a vertex from an n simplex, you get an n-1 simplex, as I will show you in this example. Here, if you take the boundary map of the one simplex, for example, you just first delete V0 and you get V1. Then you delete V1, but not because you're alternating, you get minus V0. But for the triangle case, for example, you delete V0 first, then you get V1, V2, which is a one simplex here, the line segment. Then you delete V1, but because it's alternating, you get minus V0, V2, which is again a line segment here. And finally, you delete V2 and you get V0, V1. And it goes like this for any dimension, not this boundary map. Here's a quick lemma. If you apply the boundary map 2 consecutive times, then you get a trivial map. Because like a boundary is trivial, 0. How do you prove this lemma? You just write that definition. You just apply 2 times. This is a sigma, this is a unchained, for example. And if you look at this, these two sound almost identical, but there's a minus sign difference between them, so they cancel out and give us a 0. So yeah. What do we have? We have free abelian groups consist of n chains here, and we have boundary maps defined on them. So we get an infinite chain, infinite group chain. And this lemma is actually equivalent to the fact that image of boundary n plus 1 is a subgroup of kernel of boundary n. And why is that true? Because if you take an already image element, then you map it again. It has to go to the 0 because you are mapping the same thing 2 consecutive times, so it's in the kernel. And since it's a subgroup, you have proved that it's a subgroup, then we can define our homology group as kernel coordinated by image. And since these are all abelian groups, we don't need to check any normality or something to quotient out. And this is the proof. This is the definition of simplish homology. And going back to our torus case, maybe I can show you just an example. That y is h1 is z squared, for example. So h1 of the torus is defined as boundary 1, kernel boundary 1 over image boundary 2. Definition. But what is kernel boundary 1? So for example, we have three one simplexes here, A, B, and C. And if we map them with our boundary map, we get V minus V again, which is 0 for A. And B, for the again V case, we get V minus V, which is 0. And it's the same as C. So our kernel actually consists of all one simplices. So it is just Z squared. We can write it as this notation A, B, C. The free abelian group consists that with 3 representatives. There will be a balancing or something. And what is our image boundary 2? Well, we need to look at the images of U and L. If you look where U goes, it goes to A plus B, but minus C, because of the orientation of the thing, you need to go counterclockwise. So, and the same thing as L as well. So we get the free abelian group generated by A plus B minus C. So if you calculate this quotient, this will turn out to be I152 Z squared. So this is why, as you can see here, this is why for the n equal 1 case, we have Z squared as the simplified homology of the torus. So using this definition of the homology, you can calculate each group for any n like this, and you get this result. So yeah, this was an introduction to homology. And I want to go back to our theorem. First of all, just a quick note: any homotopic self-map on X induces the same self-map on H and X. Now, the maps on X induces maps on homology groups, and if you have homotopic maps, then you will get the same map, which is true because homology is a topological invariant again. And we're going to define the Lefschetz number here, using the alternating sum of the traces of the F star on homology groups. You may ask how do you even get a trace? Like, is this a matrix or something? Well, it's a function on abelian groups, and we know that abelian groups have a finite and free part, and we can just quotient out the finite part of it, which the finite part is called torsion. So we can just quotient out the finite part, and we get a free abelian group then. And now then this F star becomes a map, something like Z, that goes from Zm to Zm. We only consider the free part of our building groups. And you can represent that map using a matrix with integer entries, and you can take trace of it. So that's how you define the trace of F star for any n. And yeah, this is the definition of Lefschetz number. In particular, when F is the identity or homotopy to the identity, then like all F stars here will be just identity morphisms. Well, and when you take the trace of the identity matrix or identity morphism, then you will get the dimension of the matrix, which will give you that the Lefschetz number of that function is actually equal to the Euler characteristic of the space, where the Euler characteristic of the space is defined like this. So each trace reduces to the rank of the homology. We're going to use this fact a lot throughout this presentation. So going back to our theorem statement, quickly, there's like our theorem talks about a space, a retract of a finite simple complex. So what is a retract of a finite simple complex? I don't want to get into too much details, but it is similar to CW complexes, but with additional restrictions. But I want to tell you that every compact locally contractible space that can be embedded in Rn for some n is a retract of a finite simple complex. So there are like lots of spaces here in this category. And also this includes compact manifolds and finite CW complexes. So we're talking about a lot of spaces here. Going back to the conditions of the theorem. Here we said every compact and local contractible space, right? Why do we even need these statements? Why do we even need these conditions? The compactness property is essential because if our space is not compact, then our theorem is not true. We can find a counterexample really quickly. If we take our space as R and a translation, which is homotopy to the identity, then our Lefschetz number is 1. But because we're translating on R, there are no fixed points. So our theorem is false for this case. And for the local contractibility case, it's a bit more complicated. You get two concentric circles and a line between them. You take a map that rotates the circles and translates the real line between them, which is again homotopy to the identity. And it has no fixed points, but if you find the Lefschetz number, which is again equal to the Euler characteristic, it is 1. And it is non-zero. So our theorem is not true for this case as well. So we need these two conditions, the local contractibility and compactness conditions, so that our theorem becomes true. I want to quickly talk about Brouwer's fixed point theorem, which we can say that Lefschetz fixed point theorem is actually a generalization of the well-known result Brouwer's fixed point theorem. What does the Brouwer's fixed point theorem tell us? It says that any self-map of the disk of any dimension has a fixed point. This is true since for any contractible space, the homology groups of the dimension higher than 1 is trivial. So to prove Brouwer's fixed point theorem, we can assume Lefschetz fixed point theorem and apply it. If you look at this sum, because our disk is contractible, the homology groups of dimension higher than 1 is trivial. So this sum actually collapses to only one component, which is F star, the trace of the F star on H0. And H0 is about connected components of our space, and our disk has only one connected component. So this is a trivial map, and the trace of it is just 1. So since we have assumed the Lefschetz fixed point theorem, we can apply it now and conclude that there must exist a fixed point. So yeah, this is why Lefschetz fixed point theorem is a generalization of the Brouwer's fixed point theorem. Yes, but we still need the Brouwer's theorem to prove the Lefschetz one. And I'm gonna give you a quick proof of the Brouwer's fixed point theorem using our homology knowledge. So yeah, we're gonna take a self-map H on Dn, and we're gonna assume that it has no fixed points to get a contradiction. So because it has no fixed points, then we can take Hx, and they are different points because it has no fixed points. Then we can take the line segment between them. And this line segment has to intersect the boundary of our space, which is Sn-1. Using this method, we can define the retraction map R that goes from Dn to Sn-1. And it's a diffraction map because if we just restrict our function to Sn-1, it's an identity function. It's a diffraction map. But the subtraction map induces the map, as you saw, the maps induce homology, induces maps on homology groups. It induces a map on HN-1 Dn to HN-1 Sn-1, and it's a surjective map because it's a reflection map. But this being a surjective map is contradicting because HN-1 Dn is trivial. It's a trivial group because Dn is contractible, and HN-1 Sn-1 is just that because Sn-1 has an n-1 dimension hole in it and nothing else. So we somehow found out find a surjective map that goes from trivial group to Z as a contradiction. And hence our first assumption was wrong. So self of H has to have a fixed point. Going back to the Lefschetz theorem, I'm going to give you a quick lemma again. It's a bit of a technical lemma. And this is where the magic happens, because these homology groups are actually smaller than the cell structure groups here. As you saw from the definition of our homology, it is kernel over image, and the kernel is again a subgroup of the cell structure thing. So homology is like very, very smaller than the cell structure group. But even though it's smaller, when we take alternating sum, things cancel out and they become equal. And this lemma can be proven using a short exact sequence that looks like this. Maybe you are familiar with them, but it's a bit technical, so I don't want to get into too much details about it. We're going to just assume it for now. And to finally prove the theorem, let's see. So why does Lefschetz number being non-zero implies a fixed point? Well, we get this equalities between 1 and 2 using our lemma. And this trace, this sum being non-zero means that there must exist a non-zero element in the sum for some n dimension n. And well, a trace being non-zero implies there's a simplex S with f star S mapped to itself. So there must exist a simplex that is mapped to itself. Since simplices are homomorphic to disks, as we saw, like the triangle thing is, for example, homomorphic to 2 disks, or the tetrahedron thing is homomorphic to 3 disks. We can use Brouwer's fixed point theorem to conclude that there must exist a fixed point in the simplex that gets mapped to itself. And this is our proof of the theorem. So, yeah. I'm going to just quickly talk about the converse of the theorem. It is false, converse of the theorem. And here's a quick counterexample to it. We take our space X as a torus and take the identity map on it. Since we are talking about the identity map, the Lefschetz number is again equal to the Euler characteristic of the space, which is defined as like this. But we know the homology group structure of the torus here. Yeah. So we're taking alternating sum on this. We get 1 minus 2 and again 1. We get the 0. And so this implies that the Lefschetz number is 0. But obviously, the identity map has infinitely many fixed points on it. So the converse of the theorem actually is false, and this is the counterexample to it. And yeah, that was all for me. This is my reference, only one. I use only one book.
Thanks a lot, Doran. Are there any questions?
Let me